Alright, welcome to AP video 15.2. This one's on buffered solutions. We're going to define what a buffer is and explain how they work, and then we're going to start calculating the pH of buffers if you know what the buffer is made of, and what happens when you add some strong acid. In that case, that's pretty much H+, that's what we care about, or when you add a strong base, which is essentially adding in the hydroxide ion. So, let's get going. Okay, so a buffer or a buffered solution is a solution that resists changes in pH when a small amount of a strong acid, the H+ there, or a strong base is added. So adding those things typically will increase pH a lot. But if you have a buffered solution, a buffer, those solutions resist changes in pH. All buffers consist of the conjugate acid-base pairs. So your choices here would basically be you have a weak acid and its conjugate base, in this case that'd be the A- of HA, or you'll have the weak base and its conjugate acid. Now that's the BH+ version there. I guess the big thing is if you have a conjugate acid-base pair, they must share a common ion. That's what makes it a conjugate acid-base pair. Okay? Just a reminder, conjugate acid-base pairs only differ by the gaining or losing of a proton. So if you have HA, if it loses a proton, what's left over is A-. So these conjugate acid-base pairs only differ by the gaining and losing of a hydrogen ion. Okay? Now here's how a buffer works. So in your notes, I want you to kind of draw a line to separate the examples that I have I've given to you here. So here's kind of like the general example, and here's a very specific example you can kind of work with. So in general, we have a weak acid, and we have a salt here that contains the conjugate base. So I don't really care about sodium, it's a spectator. But here's the conjugate base A-, so it's HA and A-. In this specific example here, we have acetic acid and we have sodium acetate. Again, this is a salt, so you get rid of the sodium there, and there's the conjugate base acetate. So remember, conjugate acid-base pair, you need a weak acid and its conjugate base here. Now, when we add a strong acid here, and we're basically supplying that ion, the H+ ion, when it is added, who's it going to react with, do you think? Is it going to react with the acid, or is it going to react with the base component here in your buffer system? And what we should always know is that acids react with bases. Acids will react with bases to do some exchanging. So in this case, the strong acid will react completely with the base part. That's going to be the A- portion. And when they react together, it's going to produce the weak acid portion. So basically it's going to turn the HA back into, or the A- back into HA. So therefore, when you add a strong acid, what's going to happen is the pH is only going to increase a little. Okay? If you have a buffered solution, I chose the wrong word there. pH is going to decrease a little, because when you add a strong acid, that makes the pH go down, more acidic. So now we kind of explained that the strong acid here reacts with the base component. Let's actually write that out. So the strong acid will be represented as H+. It's going to react with the base component of the buffer, A-, and we'll use a one-way arrow here, and they're going to react to produce HA. In the specific example here, the H+ will react with the acetate portion here, and they're going to produce the weak acid portion. So I guess the big thing to notice here is that when you add a strong acid, it reacts with the conjugate base here and turns it into a weak acid. So buffers, what they do a really good job of is they take strong things, in this case a strong acid, and they turn it into a weaker form, which therefore does not change the pH very much. Okay, let's look at the opposite example. When we add hydroxide this time, hydroxide is going to react with the acid component because acids react with bases. So OH- strong base reacts with the weak acid and is going to turn it into the A- form. It's going to take the hydrogen from the acid and turn it to the conjugate base. When you add strong base, that should increase the pH a little. I'm going to use the up arrow there to represent increase. So when you add a strong base, the pH will increase a little. So this time, when you add a strong base, OH-, it reacts with the acid component, HA, and is going to turn it into water. Part of it, it's the OH, and the H forms water, and what's left over is A minus. So you turn a strong base now into a weak base. So again, a buffer does a good job of neutralizing strong bases by turning into weaker bases. In this specific example here, the hydroxide will react with acetic acid. It's going to form water, and it's going to form the conjugate base C2H3O2 minus. Strong base turns into a weak base in a buffer. Okay, real quickly, here's how a buffer works when you have a weak base and it is conjugate acid. So this represents, it's probably easy to see the other one first. This here is a salt, ammonium chloride. It's an ionic compound, and then essentially chloride came from a strong acid, so therefore this is a neutral ion, does not do anything. This came from a weak base, so this is the conjugate acid here. So here's the conjugate acid of a weak base. Weak base and its conjugate acid. So again, we'll draw our lines. So when you add H plus, strong acid, it's going to react with what component? The weak base or the conjugate acid? And the answer is acids react with bases, so it's going to react with the base portion there, and it's going to turn it into its conjugate acid form, BH plus. When you add a strong acid, that should cause the pH to decrease a little. And we say a little because buffers resist pH changes, so they only change a little. So here we go, we say H plus from the strong acid will react with the weak base and turn into its conjugate acid form. So you turn a strong acid into a weak acid, the conjugate acid form. In the real example, H plus will react with NH3 to produce NH4 plus. And then going the other direction here, when you add a strong base here, strong base is going to react with the acid component, so that's the BH plus here, get rid of the chloride. Let's react with that portion there. And it's going to steal that hydrogen and turn it back into BH. This will increase the pH a little. And here's why. So when you add hydroxide, it reacts with the acid component, BH plus. It steals that hydrogen, turns into water, and what's left over is the weak base. So a strong base turns into a weak base. In the real example, hydroxide reacts with NH4 plus to produce water, and the weak base form NH3. So a strong base turns into a weak base. That's how buffers work. Now, next I'm going to show you is a little trick, and I think you're going to like this. It's called the Henderson-Hasselbach Equation. So on your paper right now, in the space provided, write this on the left-hand side, this equation on the left-hand side, and then draw a little arrow to the right-hand side. And then I'm going to go through a little derivation, which you don't need to write down, and the very end equation, you can box that off and write that in right here in your notes as needed. So copy this in quick. Okay, so here's what we're going to do. We are going to take, I'm going to take, the negative log of everything. And when I do that, I get negative log Ka is equal to the negative log of H plus. I'm going to do a little maneuvering here. And we're also take the negative log of the A minus over HA portion here. Okay, so just a little splitting up here. It's okay what I did there. Basically, when you take the negative log, remember, that means P. So negative log of Ka means pKa. And the negative log of this portion here of H plus, that means pH. The other part there, I'm not really going to change too much. Okay, so I just took the negative log of everything, it turns into this. And just rearranging the equation so there's no negative signs, we end up with pH equals pKa plus the log of the base, which is A minus, over the acid, HA. This is the conjugate base of that acid. This is what we call the Henderson-Hasselbach equation. It allows us to calculate the pH of a buffer. All you need to know is the Ka of that buffer and take the negative log of it. Remember, negative log of something means P. So pKa means take the negative log of Ka. And this other part here, this is just the ratio of the conjugate base over the acid portion. So this is a really easy way to find the pH of a buffer. Let me show you. So practice problem number 5 here says find the pH of this buffer. Well, here is carbonic acid, and here is hydrogen carbonate, sodium hydrogen carbonate. This is HA, and this here is A minus. That's a salt. That sodium goes away. This right here is the conjugate base of the acid over there. So what we're going to do is use our equation now. pH equals pKa, and pKa means take the negative log of the Ka value. And the Ka value, we've actually seen this before. The Ka value, I'll just write Ka here. The Ka value is 4.4 times 10 to the negative 7th for this particular acid. And then log of the base over the acid. This is the base part. This is the conjugate base. So this is the base part. So that goes on top, 0.0300 divided by the acid portion, which is 0.0250. Alright, so punch in your calculator quick and then unpause this when you're done. Okay, and from this we end up with a pH of 6.44. So that was a really easy way to find the pH of a buffer using this Henderson-Hasselbach equation. You know what? You already solved this problem. Let's go back for a second. The last question from the previous notes. It was the exact same buffer. Okay, we did a rice table, and we went through and plugged it in here, and we got a pH of 6.44. Okay, so buffers really are rice tables here. We start with a little bit of initial amount of that common ion, and we can find the pH. But using the Henderson-Hasselbach equation, we can just plug in here and solve. So as long as you know the concentration of the acid component and the base component, that's what the Henderson-Hasselbach equation is all about. It basically shows us that this ratio of the conjugate base and the acid there, along with the Ka value, is a way to determine the pH of a buffer very quickly. Okay? Alright, now heads up. Things are going to change. We're going to start actually mixing acids and bases together. Up to this point, you've been finding the pH of acids. You've been finding the pH of bases. And I've just started to kind of mix them together slightly by doing like the common ion effect with buffers. But now we're really going to start taking an acid or a base, and we're going to start doing some neutralizations here. Whenever you start to mix acids and bases, that is stoichiometry. We need to be in moles, because when acids and bases react with each other, they're going to neutralize each other and do a little bit of conversions. So make sure you're in moles. And then when we're all done with the problem, you'll need to convert back to concentration, which basically allows us to get back to H plus concentration, because that's the key of finding pH. Okay, so please make sure you're in moles whenever you're adding acids to bases for the stoichiometry component. So let me show you here in problem 6. So it says calculate the pH of 1 liter of the previous buffer. Here's the previous buffer we were working with, and we have 1 liter of this particular buffer. Calculate the pH when 0.00200 moles of KOH is added to it. And basically, potassium hydroxide here, get rid of the potassium. This is a strong base, right? So you're adding hydroxide. Okay. Who is the hydroxide going to react with? Does it react with the carbonic acid? Or does it react with the, cross off sodium here, does it react with the conjugate base? Does hydroxide react with the acid component or the base component? And the answer is hydroxide is a base, so it reacts with the acid component here. We'll call this HA. It is going to react with the acid component. Okay, this is A minus. So let's first of all start out writing the reaction here. We're going to do a little rice table. Let's write out the reaction. So the reaction is the hydroxide, OH minus, is going to react with the acid component. We'll just say HA to, make it a little shorter. Okay. The products here, when hydroxide reacts with an acid, it's going to be an acceptor of hydrogen. So it turns into water itself, and it turns the acid component into A minus. Now we're going to plug in our initials, and the initials here are always going to be just for these two guys here. So the initial amount of hydroxides given to you in the problem is 0.00200 moles. The acid here, well, we don't really have moles here. What we have is we have the volume and we have the concentration. Okay? And I just kind of lied, I just noticed here. We actually are going to have some of this A minus because it's a buffer. We have these two things to start with. Okay? So what we're going to do here is we're going to use the volume and the concentration to find how many moles there. Remember, molarity equals moles over liters. When you know these two things and multiply them together, you can solve for moles. So it's kind of nice here because I gave you 1 liter. So 1 liter of this concentration means it's that many moles. So we actually have 0.0250 moles of this, and for over here we have 0.0300 moles of the conjugate base. So you can plug those in now. There's the moles of the acid component, and here's the moles of the conjugate base component. And for water, we don't care. So what's going to happen here is this is going to be a complete reaction between hydroxide and the weak acid. And it's a limiting reaction kind of problem. They react in a 1-to-1 ratio, so just look. Right now we have less moles of hydroxide, so all of that's going to get used up and react with this and turn into A minus. So we are going to lose 0.002 moles from both of these things. Okay, and they're going to turn into 0.002 moles of this conjugate base here. So the hydroxide here is always going to be 0 when we're done, because it's the limiting reactant. Whoever the limiting reactant is, that's going to be 0 when you're done. And then here we're going to subtract away the 0.002, which leaves us with 0.0230. And over here we gained a little bit, and now we're at 0.032. Okay, so what's kind of nice here is all we have left is HA and A minus. And whenever you have HA and A minus left over, you need to think Henderson-Hasselbach equation, because right now you have a buffer. You have this and that, and this makes a buffer. So what we're going to do here is plug in pH equals the pKa, which is negative log of that 4.4 times 10 to the minus 7th. That's the negative log of Ka, plus the log of the base component, which is 0.032, divided by the acid component, which is 0.023. So just plug and chug on your calculator, and this will show us what the pH goes to. And the pH goes to 6.50. Okay, so take a look at the previous problem. The pH started at 6.44, and by adding that small amount of a strong base, the pH rose just a little bit to 6.50. And this is how we find the pH of buffers when you add a strong base or a strong acid to them. The next problem, you're adding a strong acid. And I'd like you to try this one on your own. And I'll tell you right now, the answer at the very end here is going to be a pH of 6.32. 6.32. Okay. And I'd like you to try to get this one on your own. Just one thing to get you started here. We start with the same volume of our buffer, 1 liter. And the difference here is when we add in the acid this time, I'm having you add in a certain volume of acid. So I didn't just tell you the moles like the previous problem. I just told you right here how many moles. This time I'm giving you a volume and concentration, so use that to find how many moles of this strong acid you're adding, and try to figure it out. Okay. Last thing before you go, we are adding a strong acid. It's nitric acid. Who will the strong acid react with? Will it react with the acid component or the base component? And it should react with the base component, so HCO3 minus. So your reaction that you'll be doing for your rice table here will be the acid will react with HCO3 minus to produce H2CO3. So plug in your initials for everything, do the stoichiometry, calculate the E values here, and you will end up with an acid and its conjugate base here, which help you use the Henderson-Hasselbach equation to determine this pH in a relatively quick way. Alright, good luck.